All right, guys, we just barely finished talking about this idea of complex numbers. But before we get any further into complex numbers, I think that it might be useful for us to just flush out this idea of imaginary numbers a little bit better. Remember that a complex number is this combination of real numbers and imaginary numbers, and the applications for this, as already mentioned, are boundless. There's a lot of things that we use it for every day. There's a lot of things that you guys even use it without realizing it, just by picking up your cell phones and playing games or doing whatever else, right? But first, before we go any further, let's just dissect this idea of an imaginary number. And so, if you remember here, guys, an imaginary number always expressed with the letter I. Again, I hate that, I hate that name because it's not, doesn't give it credit. But imaginary number here, guys, expressed with I is always going to be equal to the square root of a -1. And the reason being is that we cannot simplify this any further, right? We can't take the square root of a negative number, because a negative number is the result of a positive and a negative number being multiplied together. So there's no way that we can factor that out. Now, we can factor out all the positive parts, right? But we or even multiple negative parts, I guess you could say, but we cannot simplify that further. And maybe just to give you guys another example of how we can simplify this, if we had the square root of -16. Remember, we're taking the square root here, means that we want sets of two factors that are the same. And if I come up with factors of 16, we could do this any way we want it, but I'm going to do it 4 and -4, because that's going to give me almost a solution right here. Now all I have to do is just factor my -4, because again, I want a result with this with just a square root of a -1, so that I can replace that with an I. So -4 is going to factor down to 4 and -1. Now that I've got that, I do have a set here, which I can pull onto the outside. So the square root of -16 is going to be equal to 4 square root of a -1, which we know we can substitute in this value of I for, right, that square root of -1. So I'm going to get 4I as my solution for that. Okay, but there's a couple other conditions here, or not conditions, but patterns I think you guys will notice as we work more with these, especially as we do exponents of these. Okay, so the first one I want to talk about here really quickly is I squared. I squared is going to be, remember what I is. I is the square root of a -1. And if we take that whole piece and square it, right, what happens to my square and my square root? Well, remember that the square and the square root are the opposite of each other, which means that they're going to undo each other. Or I guess you could even think of them as almost the inverse of each other, right? So my square here is going to cancel out my square root. Those are both going to be gone, and all we're left with, which is what was left inside, which is this -1. So my solution for I squared is simply going to be -1. And hopefully that makes sense to you guys, because again, that square and that square root will just cancel each other out. Our next one here that I want to talk about really quickly is I cubed. I cubed is going to be somewhat similar to what we just barely saw there, but we can break this up a little bit differently here. To make this whole thing, I think, pan out better, right? But I cubed is going to be, and let's just write this the same way, it's really going to be the square root of -1 cubed. And we could think about that. If we expand this out, I think that might make it easier. If we expand this out, we're really saying I got the square root of -1 times the square root of a -1 times the square root of a -1. And if we kind of pair these up, which we could do, since we're doing multiplication here, I could pair these two up right here. It really doesn't matter. Remember, again, multiplication is associative, so it doesn't really matter the order, and we're dealing with the same things anyways. But this is the same thing, right, as saying, the square root of -1 times the square root of -1 is the same thing as saying the square root of -1 squared, which we already know what that is, right? And then that's going to be multiplied by this last square root of -1. So now that we've solved for this piece right here already, just barely over here, we know that this is going to be equal to a -1. So really what I'm going to have here is -1 times the square root of negative 1. I can't simplify that square root of negative 1 any further, right? Which really means that I'm going to have, or we can just substitute back in our I for this, which is going to give me negative 1 I, right? And we don't ever say, it's like saying negative 1x. We don't say negative 1x, right? Because the 1 is implicit or it's implied. And so we're just going to write this as a negative I. Okay, negative I is going to be the solution for I cubed. I want to do 2 more of these just to kind of send home this idea on how we're multiplying with i's work out. So let's do I to the 4th power. Okay, I to the 4th power. Now I to the 4th power is not going to be too dissimilar from what we saw with I squared here, because I'm going to break this up. I'm going to have the square root of negative 1 times the square root of negative 1 times the square root of negative 1 times the square root of negative 1. And hopefully you're seeing that these are going to pair together, kind of like what we did before, right? And I'm going to get a set of pairs here and a set of pairs there, which I can rewrite as the square root of negative 1 squared times, that's what I'm substituting that, remember those mean the same thing, times the square root of a negative 1 squared. Well, we already know what the square root of a negative 1 squared is, right? We did that in this first scenario here, and it's going to equal this negative 1 right there. So I can replace now a negative 1 in for both of these square roots of negative 1 squares, and I would get negative 1, I'm going to put these in parentheses so it's a little more clear, times negative 1. Well, and that's easy, right? Most of us, I think, understand that one pretty easily. The fact that there's 2 negatives there, the negatives are going to cancel out, right? 2 negatives multiplied by each other give you a positive, and then 1 times 1 is just 1. And so I to the 4th power is going to be 1, is our solution there. And I think that hopefully you guys will see some sort of pattern emerging here, that our first, I squared is going to give me negative 1, right? And I cubed is going to give me negative I, and then I to the 4th is going to give me positive 1, and hopefully, again, you can see this pattern emerging here as to what I to the 5th power is going to be. And let's just expand this out just like we did with the other steps there, and see what we get. Right, if I expand this out, I'm going to get, I'm going to get the square root of a negative 1 times the square root of a negative 1 times the square root of a negative 1 times the square root of a negative 1. I know there's a lot of square roots of negative 1s here, but bear with me, guys. And same process, I can break those up into sets of squares, because I want to do that because I already know what the solution for I squared is. It's that negative 1, and that's easy to deal with. A negative 1 is easy to deal with. So let's break this up. I'm going to have one set of squares right there, right? And another set of squares right there. And then I'm going to be left with this remainder of just square root of negative 1, which we can rewrite as I if we want, but let's go further here. So I'm going to have square root of negative 1 squared times the square root of negative 1 squared times the square root of negative 1. Well, and we just barely did this piece right here, right? And we can see that from just above here, right? We just barely did that. We know that that's going to result in, our squares and our square roots are going to cancel out. So I'm really going to be left with negative 1 times negative 1, which is going to give me positive 1. So what I'm going to be left with here is positive 1 square root of negative 1. And we can substitute in for our square root of negative 1 since we can't simplify that any further. Just an I representing imaginary numbers, right? So I'm going to have 1I, which we wouldn't write 1I just like we wouldn't write 1x. We just write I. Okay, and hopefully that's making a little bit of sense to you guys on how multiplication is going to be handled when we're dealing with these. When we're dealing with these as far as addition and subtraction, we're going to handle it just like we handle any other variable. So you could treat it just like an x, for example, and maybe we should do a quick example here. So what if I had 2 sets of complex numbers? Remember, a complex number is going to be, well, before we even do that, let's just talk about adding these up. What if I had 3i plus 4i? Okay, pretty simple here. We're just counting how many of these i's do we have total. Well, we've got 3 here and we've got 4 there. And we're adding those together, which would mean that we would result in how many i's total? Well, we would have 7i, right? 7i. And hopefully that makes sense to you guys. Let's do one with subtraction. What about if I have 5i minus 2i, right? Well, same scenario here. We're saying how many i's do we have? Well, I got 5 to start with, and 2 that I'm taking away from it. So how many would I have left if I take 2 away from 5? I would be left with 3i. Okay, let's take a look here before we move on to the next part of this and do a complex number. Right here we're just adding imaginary numbers, but let's talk about what's going to happen when we add complex numbers. Remember, a complex number is going to be a combination of real numbers and imaginary numbers. So an example of a complex number could be 2, which is a real number here, plus 3i. So I've got my real number portion right here, 2, and my imaginary portion right here, which is 3i. And I could add that piece, that whole thing, so let's put parentheses around that so we can identify our complex number here, and add that to 4 plus, I don't know, 5i, all right? 4 plus 5i. Okay, now because we're doing addition between these, we really don't need to have those parentheses there at all. I simply wanted them so that you guys could understand that we're just add or identify those two complex numbers. The first complex number here, the 2 plus 3i, and the second complex number, 4 plus 5i. When we add these together, we're going to do these just like we do any bit of algebra that we've done with linear functions or quadratic functions. We can combine like terms, and so let's talk about our like terms here. We've got two different sets. I've got my real numbers as one set of like terms, and then I've got my imaginary numbers as another set of like terms. And because addition is associative, we can actually group those like terms together and rewrite this now as 2 plus 4, my real number parts of the complex number, and then add to that, of course, my imaginary components, which are the 3i plus 5i. And then this is going to handle just like anything else, right? Well, I can combine these pieces right here, my 2 and my 4, my real numbers, which would give me 6, and I can combine my 3i and my 5i, which would give me 11i, and that would be my solution for that piece. Okay, hopefully that makes sense, guys. As always, if it doesn't, come grab me. We can go over anything and answer any questions that you guys have. Okay, let's take a look now at what happens when we handle multiplication. We kind of covered that a little bit when we talked about squaring, cubing, and whatnot of these functions, or not of these functions, of imaginary numbers. But let's just take a look at this really quickly and discuss what's going to happen here. Okay, so in this first problem here, we have the square root of 2 times I, and then that whole thing squared. And I would hopefully remind you guys, and hopefully you remember too, actually, that the distributive property of exponents over multiplication, right? So we can distribute this square through to both the components inside here because we're multiplying. If we were adding, we couldn't do that. But remember that multiplication and exponents are just another way of communicating the same information, which is multiplication. So we can do that with those. And so if I distribute that through, I really am going to have 2, or the square root of 2 squared multiplied by I squared. Okay, and we've kind of seen what happens multiple times now when we square a square root. Those are the opposite of each other, right? So they're just going to cancel each other out. So I would only be left with what's in the middle of this, and what's in the middle of this is just, or in the inside here, is just my radicand, which is 2, right? So I'd be left with 2, and I'm going to multiply that by I squared. And we spent a bit of time actually just barely going over this, and I squared, hopefully this makes sense to you. Remember that, let's take a look at this real quick, that I is really the square root of a -1, and we're squaring that. So my square and my square root and my square just cancel out, and I'm left with only that -1 on the inside, right? So I'm going to have 2 times a -1, which is going to give me -2. Okay, I hope that's making sense, guys. Let's take a look at this next one here. This is 3i times 3i, which, if we wanted to, we could actually write this as 3i squared right? But we don't have to. And another way, and also remember that, multiplication is associative. Really, when I'm saying 3i, I'm saying 3 times I times 3 times I. And because multiplication is associative, I can rearrange that and multiply the pieces together that I want. In other words, I can multiply my real number portions together and then multiply my imaginary components together, okay? And if I did that, I would get 3 times 3, which is going to give me 9, and then I would get I times I, which is I squared. And we just talked about that. We already know what I squared is. We can just go ahead and substitute that value in, which it's a -1, right? So -1 times, or 9 times -1 is going to equal -9. Okay, again, hopefully that's making sense to you guys. I want to do just one last example here, and I didn't bring up a graph of this, but hopefully it'll be okay. We have this function here, and I'll just read this. It says, using this new notation, the solutions to the equation x squared plus 4x plus 5 equals 0 can be written as -2 plus I and -2 minus I, and the factored form of x squared plus 4x plus 5 can be written as x plus 2 minus I times x plus 2 plus I. So essentially what they're saying here is we've got a function, this quadratic function right here, and this quadratic function has no x-intercepts. But we can still write it in factored form, right? We can still write this in factored form, but instead of, remember your factored form would be your, y equals a times x minus b times x minus c, where your c and b values here are the x-intercepts, right? The x-intercepts. And in this case, because we don't have real x-intercepts, we have these imaginary x-intercepts, and so we're replacing in that these two complex numbers that represent those x-intercepts in the imaginary plane. And that might sound a little fancy, but just understand that we can still plug those in, and or if we put this into that quadratic formula, we would get as our solutions -2 plus I and -2 minus I as my x-intercepts, because again, they're not real, right? So we're going to get these complex numbers. But on the flip side, though, I can take this same information and work backwards. If I have this in factored form like they provided right here, if I have this in factored form, I can go back to standard form using this notation, right, and just distribute through. And that's the part that I want to do with you guys, because I think it's a valuable little lesson here. So let's rewrite this. I'm going to have x plus 2 minus I times x plus 2 plus I. Now, remember, guys, when we did, whenever we have these in factored form like this, if we want to distribute it out and get into standard form, we got to use that FOIL method. And that might seem a little more confusing here because we got 3 pieces instead of 2 in each, but understand that the the same principles apply. We want to take each piece here and multiply it by each piece here. So I'm going to take my x, my 2, and my -I, and multiply each one of those by each of these over here, by my x, my 2, and my +I. So let's go ahead and just do that. So first things first, and maybe let's switch colors here so that we can stay a little bit more organized. Let's do our x's in a green. How about that? Okay, so I'm going to take this x, I'm going to multiply it by my first term over here, which is going to give me x times x, or in other words, x squared. Okay, and then my x times my second term, which is 2, so I got 2 times x, which gives me 2x, right? And then my x times the last term over here, which is I, right? So I would get xi. And that might seem a little confusing, but remember, we can't simplify this any further. It's just like if I times that I by 3, I would have 3i. In this case, I just got xi. X just represents some number, right? And so I'm going to have over here, I'm going to put a little bit of space here, I'm going to have plus xi. Okay? And so let's go on to our 2. Same thing here. I'm going to take my 2 and multiply it by all the pieces over here. So I'm going to have 2 times x, which gives me 2x. And then I'm going to have 2 times 2, which gives me a positive 4. And then I'm going to have 2 times my last term, which is I, which is going to give me a plus 2I. That's kind of hard to see. I should have done a different color. Sorry. And I'm kind of breaking these up so that we're grouping them together in like terms, and I hope that makes it a little bit easier as we go forward. And let's do our last piece here, our last term, that negative I. So let's take this negative I and multiply it by each piece. I'm going to take negative I and multiply it by x, which would give me negative xi, and my negative I and multiply it by 2, which is going to give me a negative 2i, and then my negative I times my I, which would give me a negative I squared. Well, remember, guys, we already know what this I squared is going to be, right? We already know what I squared is going to be. We've done that before, and so I can substitute in here for this I squared. Remember, again, I squared is square root of negative 1 squared, which equals negative 1. So I can plug in here a negative 1. So I would have, instead of this I here, I squared, I'm going to have a negative 1. Okay, so let's go ahead and take a look at this one last. If I'm subtracting a negative 1, right, I'm really adding a negative 1. So let's put that over here with our regular numbers. I'm going to put my positive 1 right there. Okay, and that's all of our pieces. Now all we got to do is just combine like terms and solve this. Okay, so there's only one set of x's to deal with, and that's just this x squared at the start, so we can just drop that straight down. I get x squared, and over here I'm going to get, I've only got 2 sets of x's. Sorry, x squared is what I meant before if I said x's, excuse me. So, and then on my x squared, or x's, I've got just 2 sets of those, and they're 2x each, so 2x plus 2x is 4x, and then I'm going to have 4 plus 1 for my real numbers, right, which is going to give me plus 5. And right there, you see, we actually have that equation that we started with. We still have some more stuff here, and let's see what happens. But we have that equation that we started with, or that we predicted that it should be once we were done. I've got xi minus xi. Well, that's just going to leave me with 0, right? And then 2i minus 2i, which is 0, and then we already got rid of that piece. So I don't even need to write that in. What I'm left with is this function right here, which is what we predicted it would be. And it holds true that if we use these imaginary numbers to express the factored form of a quadratic function with no x-intercepts, we can still put those numbers in and distribute through and come back to the original equation. And in that way, we've proved that those imaginary numbers do work, they do exist, and they are usable throughout nature. Hopefully that's made some sense, guys. Rewatch the video if you got to. And as always, if you guys have questions, just come and let me know, please. Thanks. Have a good one, guys.